I stumbled upon a new paper written by Professor John Austerhout from Stanford University. The paper summarizes a new protocol that replaces TCP, which is one of the most abundant, if not the abundant protocol that is used everywhere. And if it's not directly used, it's probably used by your application right now, even if you don't know it, right? Like HTTP uses TCP. Yeah, I know HTTP 3 does switch to QUIC, which uses UDP, but a lot of applications, SSH, SMTP, all of these protocols directly uses TCP as a protocol, and it's been very popular for years. So why change? Apparently, when I read the title of this paper, I was skeptical. We need a replacement for TCP in the data center. Emphasis in the data center here, because don't get defensive like I did when I first read it. It's like, someone who want to change the way we do things, networking and backend engineering. I try to be objective and look at the actual paper and see the original problems that TCP has, because we agree, right? TCP is not good for everything. We know that. That's why we have QUIC. That's why we use UDP directly, especially for gaming, for video streaming, things like that. Because we know that TCP is great, but also it has limitations because it was designed, it was ossified is the right word, and it's very hard to change, but people worked around it. So in this episode of the Backend Engineering Show, it's going to be a little bit different. It's going to be a little bit longer, so get a drink, relax, and let's enjoy this show. I think it's going to be a good discussion, really. I think it's a good paper. Do I think this new protocol that is called Homa, by the way, a very common Persian name, like that's how I know it, because my mom is, my mom's side is Persian, so that's a very common used name. And I think Homa is some sort of a mythical bird that always flies and never lands. I don't know the history, but I don't know if it's inspired by this mythology or not. But regardless, I think this is going to be interesting. Let's just keep an open mind, read it through. Obviously, I have my criticism as usual. We'll try to keep an open mind, read it through. Let's have fun. Let's jump into it. Welcome to the Backend Engineering Show with your host, Hussein Nasser. Today, we're gonna read this summary paper. That's not the actual paper for this new protocol that attempts to replace TCP in the data centers. Again, very important to emphasize that in the data centers. In the data center, everything is tightly tucked in together. The latency is almost latency when it comes to networking is in microseconds, hundreds and microseconds, or even less than that, right? In switches, like nanoseconds, hundreds of nanoseconds. So they invest a lot in this, making these equipments as fast as possible, unlike the internet, which is like Wild West. And obviously there is latency, there is limitation when it comes to the MTUs used during the maximum transmission unit. We don't have these limits in the data center. We are so fast, and TCP is apparently slowing development of applications on the data center. Let's find out. I never worked in the data center. I don't know the challenges of the data center. That's why I'm taking the word of Professor John here, and the references he references. Let's get started. We need a replacement for TCP in the data center. Let's read the abstract. By the way, I downloaded the PDF and I started highlighting the important parts that I believe it's important, because I can't go through the whole paper, obviously. It's not that long. It's just 6 pages, But I only highlighted the interested parts that I want to discuss here, right? Abstract. In spite of its long and successful history, TCP is a poor transport protocol for modern data centers. every significant element of TCP from its stream orientation to its requirement of in-order packet delivery is wrong again for the data center. Professor John emphasizes on this statement. It's just for the data center. If you're using it on the internet, don't change it. So think about stream orientation. So when we talk about TCP, now the idea of TCP sits on top of IP, and IP has packets. And if you want to send data through TCP, you ship them into segments, right? No mention of segments at all here, which is something I have to criticize. It's very hard not to talk about TCP and not mention very critical concept of TCP, which is the segment. Not a mention, not in the original paper, not in this one. Zit, nothing. So TCP has this idea of segments, and segments will have the TCP header, which includes the port, information about congestion control, other information as well. Can't remember right now. Sequences, window sizes, stuff like that. And this is where the headers actually, all the information, these segments carries your data. So if you send a bunch of data, let's say I want to send a whole Word document, bad example, but that will be try to send into this TCP socket. When you create a connection through TCP and you just stream that whole Word document into the socket, your application doesn't really know about this concept of segments. The kernel takes care of breaking things down into segments, right? Sometimes I guess you can have access to those, but you just get a bunch. This will eventually be broken into multiple segments and will be shipped. Each segment will be sequenced with a number. Okay, segment number 1, right? The first part of the document, second part of the document. So how many segments? It really depends on the MTU, the downlink layer, obviously, how much your Wi-Fi connection can handle, how much your LAN can handle, and that is basically the maximum transmission unit, your NIC, your network card, effectively. And that carries on to the maximum, the PDU, which is the packet size in the IP packet, which obviously translates to the maximum segment size, right? So you can send up to maximum segment size worth of content. But all of this is called a stream. It's just a stream of data. It's just in sequence packet. So if you think about it, there is no concept of, request in TCP. You send the Word document, how do you know if it actually arrives, right? The application has to decide that, because it doesn't know. The transport protocol doesn't know about this discrete, boundaries of your messages, as the paper calls it, or request. Even the HTTP request. When you send an HTTP request through TCP, there is no concept of a request at the TCP layer. You send a bunch of bytes, the bytes goes, right? And the HTTP request becomes get/HTTP11. You put the headers, all of this becomes a byte string, and then that byte string is shoved into the TCP layer. The kernel might use 1 if you're lucky. I think the 1500 is the maximum segment size in the internet by default. And the data center is way larger than that, obviously, right? Because they have control of all this equipment. They can increase that. And that basically controls the frame at that data link layer. So we're still in the abstract, and I still didn't continue. I have to shut up and read. So from its stream orientation to its requirement of in-order packet delivery, it has to be in order. Because you're sending a stream, it better arrive in order. Otherwise, the Word document or the request, the actual content of the request will be arrived out of order, right? So that's why when you send multiple requests on the same TCP connection, you have no idea at the server side where the first request starts, where the second request ends. We don't have that knowledge, right, at the transport layer. The application has to start receiving everything, and then it says, oh, okay, this is request number 1 because it ends in a new line or whatever the HTTP standard says. And then the second request starts right there. So that's what we have here. We have in-order packet delivery. It is time to recognize that TCP problems are too fundamental and interrelated to be fixed. The only way to harness the full performance potential of modern network is to introduce a new transfer protocol into the data center. Homa demonstrate that it is possible to create a transport protocol that avoids all of TCP's problems. Interesting. Although Homa is not API, I keep saying Homa, because that's in Persian, that's how we pronounce it. It probably pronounce a different thing. Homa, might be something else, but I'm gonna say Homa. Although Homa is not API compatible with TCP, it should be possible to bring into this is really big, right? If your application is running on TCP on top of TCP directly, then you cannot use this. You have to rewrite your whole application to use Homa, right? Because it's a different API, right? There is no write or read. The whole thing is different. It's not as simple as it is. Maybe they probably, when they say it's not API compatible, that means it is literally, it's not, because the whole thing changes. We're gonna find out. The paper doesn't detail this, and it doesn't really, oddly, doesn't even mention the header, how it looks like, nothing. Right? I tried to, as much as possible, pull information. There is no concept of ports, as far as I've seen. There is no concept of ports at all. They just say, hey, host connects to a host. Why do we need ports? They just completely removed that concept altogether. So they saved on the header sizes of the, the messages that they send. I gotta admit, it's clever. They are reinventing the whole wheel here, right? So it's scary for us. It's like something new. We get scared, of course. But yeah, it's courageous, might I say. Although Homa is not an API compatible. Okay, we read this. Okay, let's read it. This is the introduction. I'm gonna read just this part. I'm going to discuss. However, data center computing creates unprecedented challenges for TCP. So here's they focus on what's so unique about data centers here, right? The data center environment with millions of cores in close proximity. Focus on close proximity, you guys. Close proximity. They are so tucked in together. This is not a solution for the internet. Don't bring this to the internet. I don't think it will fit in the internet, to be honest, right? With the way I've read the design, there is a lot of chattiness going on, especially with the unscheduled packet and the scheduled packet, and the receiver has to say, hey, go ahead and now you can send it. Oh, you can wait. Oh, go ahead and send it. There is a lot of chattiness. I don't know if it will work in the internet at all. With millions of cores proximity, individual application, harnessing thousands of machines to interact on microsecond time scale. So this is, the latency is so tiny between the machines. So we are burdened by the TCP protocol. Could not be envisioned by the designers of TCP. Yeah, the TCP is designed 40 years ago. They didn't know that. They didn't know that we're gonna reach this scale. So, I mean, what they built is amazing. That it actually survived 40 years. So I'm gonna jump in here and read the requirements. Okay, obviously this is visible, and I can disappear. That's all right. If I'm covering the page. Requirements. What are we trying to solve here? Before discussing the problem of TCP, let us review the challenges that must be addressed by any transport protocol for data centers. Again, reliable delivery. The protocol must deliver data reliably from one host to another in spite of transient failure. So they're not taking that away. There is a big difference between in-order delivery versus reliable delivery. So we're talking about retransmission here. If something failed, we have to know that it failed, it was dropped, and we need to send it again. Reliably, we have to deliver that, no matter what the consequences were. So here the throughput is, the concept of throughput is like how many units can be delivered in X amount of time. So let's say I can process 1,000 packets, IP packets that is, in a given second, right? Versus someone else can process 10,000 packets in a second. So their throughput is better than mine. They have more throughput than I do, right? Why? Because I take more time processing each packet compared to there, right? So you want to increase throughput, you need to reduce time spent in each packet, thus increasing the throughput. But that's usually called the data throughput, as they call it here, right? What they care about is actually a higher level of throughput, which is the application level message or request. So what does it mean? Even if you say 1,000 packet, how many requests are those, right? If you're sending, it doesn't really mean 1,000 packet doesn't mean 1,000 requests. Not at all. It could be 30, right? Depends on the sizes of the request, right? So throughput here is completely different, because each request or each message, I keep saying request, but you can translate it to a message. They use the word message extensively here. It's very abstract, but think of the message as a request when it's going from the sender to the server, right? And as a result, how many requests can I send in a second? How many requests can you process? That is a very important metric in proxies such as Nginx, Envoy, HA proxy. How many requests can you pull and process? And that obviously depends on the protocol at the layer 7, right? Is it HTTP? Is it HTTP2? Is it gRPC? How many requests can you process? And that is another concept that is a requirement here. The ability to send large number of small messages quickly. So that's one of their requirement. They're gonna, when you notice the theme that you're gonna notice in this paper is they focus on messages, and they're short messages to be specific. I think they define what do they mean by short messages, like within the kilobytes, right? Which is, I believe, it's very common, especially in microservices. You're probably going to make a small request and a large response, or maybe a large request and a small response. Usually requests are smaller than responses, usually, you know. I can't think of an example where a request, I guess if you send like you're writing something, hey, I'm posting a tweet, right? So the request in this case, so I take it back. The request is large, the response is tiny, right? But short messages are often, in this case, the response is short. So they want to prioritize short messages. TCP really works really bad when it comes to short messages. Just because, what does it mean, a short message, right? A short message is, I don't know, maybe, let's say 200, 300 bytes. You can fit that in a segment, right? And you might say, well, short messages to fit in a single segment at the client side, some clients can delay sending that segment and wait until it actually fills up to fill up a maximum segment size, the whole segment, you know, because it's wasteful. You're going to see this theme with TCP. It's never send a single byte in a message, in a segment. Always wait to fill it up, right? That's why most implementations today disable this behavior of waiting to fill up segment, which is called Nigel algorithm. Curl back in 2016, they just disabled that altogether. No, it's like, I have 300 bytes. Why do you want me to wait? And again, it's not just always waiting. It's just if there is acknowledgements, right? So that's, I guess, part of the things that were kind of Frankensteining on top of TCP. That makes sense, right? So I get that. Let's continue. Congestion control. So what is congestion control? So obviously they don't explain any of these concepts, right? They assume you know, and that's my job here, to kind of explain and illustrate and demystify anything that is not clear. Because when I read this, obviously some of the stuff I didn't understand, some of the stuff I did, and spend some time to kind of, I might get some of this wrong, obviously, but oh well. Well, that's part of it, right? Congestion control. So congestion control refers to, you know, TCP has two control, if you will. There is a flow control at the receiver side, where it says, okay, the host that you're sending to, how much they can handle, how much buffer they have to receive data, the host itself, how much bandwidth those guys actually have, you know, at that application side. And that's called flow control, receiver flow control. And there is another level of control, which is congestion control, which basically usually describes the middle network. Now, things like in the middle. How much can you handle in the middle, right? The routers in the middle and the switches in the middle will buffer packets. And if those buffers are full for any router of any host in the middle, before we reach the end, then those packets will be dropped, and that dropping of a packet will signal to the sender that say, hey, there is a congestion, let me slow down. And the author of Homa hate this. They hate the fact that the sender is actually slowing down rating, the transmission rate, right? And the congestion control algorithm goes like first, there's something called a slow start. By the way, I talk about all of this stuff in my networking course. Check it out. Network.HusseinNasser.com. All these fundamental stuff I try to explain, so it's all there in detail. But I'll explain it here. So congestion control starts with the TCP starts with a slow start, so it will aggressively send, and then start another algorithm, which is basically the congestion control algorithm, the normal one, where it will increase segment by segment, right, until a congestion was detected. And what does that mean? And this is where the disagreement here, the authors of the Homa paper here, they disagree, where what does it mean to be congested? The congestion in TCP says if there is a dropped packet, or sometimes there is something there, explicit congestion notification set in the IP header that router set, and layer 3 switches to be specific also, that will say, hey, I detected a congestion, I'm about to be congested. Yeah, continue. Let's slow down. So that once the congestion is detected by, if a buffer is filled, packets are dropped, timing out as a result, and the client said, hey, segment, I didn't receive an acknowledgement for this segment, there must be a congestion, I'm gonna half my window, the congestion window, the CWND, right? And then just it will go on, right? And then slows down, and that's just really bad apparently for data centers, right? It's interesting how they are trying to kind of solve this problem. They are, instead of introducing, because let's think about it, who's introducing the congestion? The sender, right? Because it's sending data like there is no tomorrow, right? It's like it's sending, and then eventually it will reach a state where the routers in the middle, there was a weakest link that cannot handle this, because the packets will get backed up and the buffers will fill, and when the buffers fill, the new packets will have no room to sit in these routers, and as a result they will basically drop the packet, will slow down the congestion. So they're flipping this algorithm. So I guess it's a spoiler alert. I'm going to explain what Homa does here. What they did is actually flip it. They make the receiver tell the sender, hey, it's okay to send now. Okay? So what happened here is in Homa, the messages will be sent regardless, a blindly send. That's what they call it. They just send anything you have, but only things that's called unscheduled packets or scheduled messages. So they're gonna send only few parts of each of the message that you're gonna send. They're gonna send the parts, the beginning of the message, which includes the message length, and that gives kind of information, metadata to the receiver. Says, this message is short, go ahead and send that. This message is long, let's wait a little bit on this. I'm gonna grant you sending these messages, but keep the rest of them. So the receiver is just orchestrating the congestion. Not really congestion, it's the receiver orchestrating the sending, right? So you're gonna see a lot of chattiness if you think about it, right? Just this thing didn't really exist. You can argue there is acknowledgement, right, coming back and forth. So they're replacing that with this concept of grants. I know. I have to continue reading. In order to provide low latency, the transport protocol must limit the buildup of packet in the network queues. Packet queues can occur both at the edge, the links connecting hosts to the top of racks. You're gonna see this mentioned a lot in the paper. Top of racks, Tor, I think, stands, not the onion router. Not to be confused with the onion router, because I've seen Tor. It's like, what does Tor has to do with this? Top of rack switches. And in the network core, each of these forms of congestion creates distinct problems, obviously. All right, this is some of the spot is like actually my favorite here, and again we are here in the requirement section, right? What is the requirement for a new protocol in the data center? So we talked about congestion control. We want to try to avoid it as much as possible. Efficient load balancing across server cores. For more than a decade, network speeds have been increasing rapidly while the processor clock rates have remained essentially static. So you see, I'm not a hardware engineer, I'm not a network engineer, right? But this actually, this makes sense, right? But I didn't know about this. Apparently, the switches are getting better, the routers are getting better, but the CPU is staying the static, the speed. Because what's his name? Moore's law, yeah, is that Moore's law? Not Murphy's law. I'm confused. Moore's law, yeah, Moore's law. That every 18 months it doubles. I think it's slowing down, but network is just keeping, the switches are keeping getting better and better. Apparently, I don't know that. So that's again, I didn't work in a data center, so any information here is new to me. News. Thus, it's no longer possible for a single core to keep up with a single network link. You have to have multiple cores. That is very interesting also. I love it. I absolutely love it. So the fact that you need multiple cores, which kind of translate to these cores must be load balanced. Like whatever the data coming into your NIC has to be shuffled into these cores in an organized manner and in a balanced manner. We're gonna read later that TCP cannot do this effectively. It creates this hotspot in a single core per connection because of this concept of connections. Both incoming and outgoing load must be distributed across multiple cores. This is true at multiple levels. At the application level, high throughput services must run on many cores and divide their work among the cores. At the transport layer, a single core cannot keep up with the high-speed link, especially with short messages. Load balancing impacts transport protocols in two ways. First, it can introduce overhead. Example, the use of multiple cores causes additional cache misses and coherence. Second, load balancing can lead to hotspots where load is unevenly distributed across cores. Right? So we're gonna see like all the packets going to one core, the other cores are not as even. And the reason we do this is for stickiness reason. We want the packets to be processed in the same core as much as possible so that file descriptors of the connection live in the processor cache and we don't have to go to the memory to fetch those information. I guess that's one way to look at it, right? That's probably why. This is the format, the congestion at the software level. Load balancing overheads are now one of the primary sources of tail latency, and they are impacted by the design of transport protocol. This is so fascinating to read this stuff. If you read it in details, that is. NIC offload. I'm not going to spend much in this because, to be honest, what NIC offload is like, that means the network interface controller, right? That means like we want as much as possible the protocol to run in the network card, the network interface controller, instead of the actual software, because it's way faster to run in that hardware environment. Problem is, I think Linux is very against that, and when I read that, I think I was like Wikipedia entries and references some articles. So the reason Linux do not want to use NIC offloading, like running software related to transport protocol in the actual NIC, is because of patches. Like, what if you want to patch this, right? How do you patch hardware stuff? And every vendor is gonna do it differently, right? So for specific data center, might be a problem. Might not be a problem because, like I say, the whole thing will be managed by one vendor, right? The whole hardware. But like, if there's a security concern, like when there's transport protocol, and you want to fix it, you want to fix a bug, like what do you do? In Linux, it's a software. You just patch it, right? In hardware, it's like, it's a firmware. What do? You have to like Yeah, it's very complicated to fix. When I read this, like, not a lot of people are in favor of NIC offloading, putting everything into the NIC because of these problems. Like, it's get very sticky to update, right? Especially if you have like a security problems and stuff like that. I don't know. I might be wrong there, but I kind of agree that it's like, yeah, NIC is faster, but is it worth it? Let's continue reading. All right, section 3. Everything about TCP is wrong. Notice that, yeah, of course, it's the language used in this paper. It's almost used in purpose to ruffle some feathers, and ruffle some feathers it did. I absolutely love it. Let's continue. This section discusses 5 key properties of TCP which cover almost all of its designs. That's actually very interesting things. We can learn a lot about TCP from this section, really. Stream orientation. The idea of having concept of stream instead of messages, actual discrete start and end right here, messages. There is no concept of messages or requests in TCP, right? You create this at the application layer. You are responsible to do that when you use TCP, and that's what HTTP does. Like, HTTP has this header called content length, and that header has been abused to oblivion with HTTP smuggling attack. Most HTTP smuggling attack happens because of the stream orientation, right? Where we don't know where the message starts and where the message ends, and as a result, where the request starts and then where the request ends. What makes it worse, HTTP, the fluid design of HTTP has multiple ways to indicate an end, right, of a request. Like, there is the content length, and there is the, what is it called, the transfer encoding, I believe, which is like, hey, I don't know, I'm about to send unlimited stuff, so just be ready. If I send like \n\r, that's the end of my transmission. I think twice, \n\r/n/n/r. That basically, hey, that ends my transmission. So just because we have multiple ways, the problem is like, what if you have content length and you have transmission encoding? The proxy will process it differently, and the back end, let's say Node.js, will process it completely differently, and as a result, hackers can smuggle sensitive requests in the second message that will be skipped completely by the proxy and will be processed by the application on the backend. This way, an attacker can call an admin API on the backend that is being actually blocked in the proxy. So that's what HTTP smuggling, and it's mostly because of the TCP streaming or orientation problem, right? They could have mentioned that, but they didn't. That's like having clear definition of where the message starts and at the transport layer immediately solves this problem. We don't have a solution for this problem, unfortunately. That's why every 2 days you see advisory, HTTP smuggling detected in Node.js, HTTP smuggling detected on Nginx. Connection orientation. Correct. The idea of having TCP needs to have a connection because, well, I don't know why it needs to have a connection. Now, after reading this, like, I'm questioning everything, to be honest. like why? Why do you need a connection? Right? Yeah, it's like I have some state, and you can store all the state in the connection. That's handy, right? You have port. That comes to the port. You connect to a port, right? This way, you can have the same host can have many applications, and the application is at the connection level. You're going to see this is a very similar thing, right, with Homa, with the concept of RPC. But Homa doesn't have connections. They removed all that together. Yeah. Because we have connections in TCP, we need to store them, and we need to store that state. And boy, if you have many connections, then you're going to need a lot of memory. There is a lot of management going on there. Bandwidth sharing, fair scheduling. So I didn't really know about this in TCP, to be honest. This is a new thing to me, fair scheduling or fair queuing or whatever it's called. I think TCP works at the segment level. So if you have a segment, if you have like 10 connections coming, like all coming to your host, right? the segments will be processed in order in a fair manner. Like, so you have one segment, this segment, this segment, this segment, and it will just round robin through them one by one, getting all these segments, right? So if your segment happened to have 1 byte and the second segment is fully loaded with content, then you will be starved. Short messages will be starved in this example, right? So short messages living in short segments will starve. That's how I understood it, at least, right? Because you'll have to wait because you're processing a larger messages segments while you have 10 short segments, right? That can be processed quickly, but instead you decided to wait and serve larger segments, right? Because of just the order. It's just fair, right? We'll go through this in details. We'll talk about it. Sender-driven congestion control. We talked about this, right? The sender dictates the congestion, right? Where we're gonna send data, send up. I'm detecting congestion. My packets are not being acknowledged. My segments are not being acknowledged. Drop. Right? So the sender, that's effectively the bad thing about TCP. In-order packet delivery. So in-order packet delivery. So the IP packets which carries the TCP segments, which have the information about the sequence, will have to be arrive in order. So even if your IP packets arrive out of order, which they will, right? At the end of the day, because it's the internet. I mean, in the data center, you can control that in a sense, not much in the internet. Then the application, the transport layer will start blocking. It says, oh, this is segment number 3. Where is 2 and 1? I'm going to wait for them. So the fact that you waited and you did not process segment 3, despite segment 3 being complete and a good message to be processed, is a wasted latency, right? So the in-order packet delivery is kind of problematic. But we solved this problem. We know about this. We have this problem today with HTTP, right? A browser wants to send 10 requests, right? How does it send 10 requests to the same host? In QUIC, we use UDP streams, which is the very similar concept. It's just UDP to avoid TCP head of line blocking. But in this case, yes, send these requests. They are completely independent streams. So the application, when we arrive at the other end, we're gonna see, oh, this is we received this segment number 3 arrived before segment number 1. Sure, yeah, they are out of order, but they are completely its own stream. So I don't care. Take it and start processing it. Do not wait for segment 2 and 1 to arrive, or request 1 or 2 to arrive to process request number 3. That's ridiculous, right? So that's basically the idea of head of line blocking. Again, it still exists if you're using a same TCP connection. That's why HTTP2 still have the idea of head of line blocking at the TCP layer. So that's one limitation of TCP right there, right? That's why QUIC solves that completely, because QUIC has independent streams, right? That's another reason why probably this paper never mentioned QUIC, because same problem. It's streams. We don't care about streams. They don't want streams. They want messages, right? So the idea of having stream, I wish that QUIC, they just thought of a concept to switch to messages, and all of this will be gone. That's it. This won't exist, right? If we just implemented in QUIC the idea of messages, I don't think it's going to be easy, but that will solve the problem, right? Technically, because that's what they want. They want messages. But if you think about it, like, they also want other things, the congestion control. We have congestion control in QUIC. We have each stream has its own congestion control limits. It's completely independent, right? So, but it's still limited by the sender, right? So that's something they don't like. I wish they really, you know what? They didn't mention anything about QUIC, and I'm mad. They really should talk about that. Because, like, why didn't you pick QUIC? I know the answer. The answer is, like, it's stream, so it won't solve anything. Why not UDP? Just build on top of UDP. Probably they want to reinvent the wheel. They don't want that concept of ports, which has it. UDP has it. They don't need this concept. Again, I'm making a lot of things up, implying, and I'm not afraid of implying things because, like, hey, it's not written here, and nothing written here, and not in the other paper. So, by the way, there's another paper right here. I'm gonna share it with you, which is the actual Homa implementation back in 2018. I read that. Nothing, no mention of QUIC, nothing. Let's read. Stream orientation. The data model for TCP is stream of byte. However, this is not the right model for most data center applications. Data center applications typically exchange discrete messages to implement remote procedural calls. Very critical. We talked about this, right? When you are in a data center, or you have like a microservice to talking to another microservice, it doesn't have to be a microservice, just the normal data center-y thing, right? Whatever things they talk about, these, Kubernetes or whatever, other, host to host or whatever applications have in their data center. These communication happen as a request response. Give me a request, give me a response. Okay. And the discrete message is the remote procedural call where, hey, I'm going to make a request, you give me a response. This means when an application reads from a stream, this is very important, that's why I highlighted it, there is no guarantee that it will receive a complete message. True, it's a stream. You read, whatever the kernel will give you. You don't know. That's why the application, the library, the HTTP library, for example, in Node.js, needs to continue reading until it gets a sense of what is reading. It's a request. It's a HTTP request. So there is no guarantee you will receive a complete message or a complete request. Think of a message as a request here, right? It could receive less than a message, a full message, or parts of several messages. Right? Because it might be the messages are so short, you might receive, 3 requests in a single read. Highly unlikely. HTTP requests are so large, right? Large is like several bytes. It's going to be a lot of bytes. So I don't know. Maybe. Yeah, if you make your request so short, like get slash the minimum, no headers, whatever the applicable headers, you can do it, yeah. Or use another protocol. TCP-based application must mark message boundaries when they serialize the messages. You have to encode your length somehow in the data. So you're wasting precious data from your side as an application to mark messages length, and you're responsible for managing the length and stuff like that. This is another important thing. If multiple threads both read from a stream, it is possible that parts of a single message might be received by a different thread. That's true, right? If the message is long, if a request is long, and you have multiple threads reading from the same stream or socket or a connection, right? Think of a connection as a stream here. So not to be confused, right? Again, this overloaded of terms is really killing me. I try to parse this paper, but professors love to use abstractions as much as possible. So that's why I try to parse it. I try my best. But a stream is a connection, as far as I know here. A TCP connection, right? So if you're reading that stream of connection of data and multiple threads are reading it, one large request might be received from one thread and the other part will be received by the other. Yikes. That is the worst case scenario, because you got my request. Can you give me the request, please? So now coordination has to happen. It's so expensive. I have to agree with that. So yeah, this is the most interesting thing. Load balancing. How do we actually solve this? The first approach used by Memcached is to divide a collection of streams statically among the thread, where each thread handles all the requests arriving on its streams. So each thread has a single stream. Why can't we just say this? Each thread gets a stream, basically, right? So one thread, one stream, one thread, one stream. This approach is prone to hots because this way you're not gonna get the two threads dealing with multiple same request, right? All the requests will be handled by a thread. But now this is a problem with the hotspot. You're going to get a hotspot problem where one connection will be so busy and the other connection is so light. So one thread will be overloaded and the other thread won't be overloaded. And that's a problem in, I guess, in Memcached. And then the second approach used by RAM Cloud dedicates one thread to read all incoming messages from all connections. So all connections, one thread. It's up to you. You can design it any way you want. What's the problem with this? So this thread reads all the messages, all the stream data, which is a bunch of segments, which now becomes a stream of data, and now dispatch messages to the thread. So that thread is responsible to breaking down the boundaries of the message. It's like, oh, you are an HTTP request. Wait, where do you start? You start here. Oh, this is where you end because your content length is this. So it needs to parse. This all takes CPU processing power, right? And then so imagine if this can be offloaded to somewhere else. That'll be really interesting. I absolutely love that part where the message boundary is handled at the transport layer. I love this. I love this in this design. It's a novel idea that I never. Yeah, because to me, I always think of messages or requests being processed at application layer. But why? Why do we have to? Why not push this down at the layer 4? Let layer 4 does this stuff. And even better, offload this to the NIC, although I don't know if it's a good idea. I think it's going to bite us in the butt in the future if we offload everything to the NIC. Right? I don't know. I don't know anything, you guys. Dedicates one thread to read all the incoming messages from all streams and then dispatch messages to the thread of the service. So the thread is doing a lot of work here. This is also much better load balancing worker because now the thread knows which thread is which thread each thread is doing, right? That's actually very interesting. So you can do a better load balancing. There is no hot spotting. Man, this is a completely different world, you know? I absolutely love this. But the dispatcher thread becomes a throughput bottleneck. It makes sense, right? It becomes a bottleneck. The fundamental problem with streaming is that units in which data is received, ranges of byte, do not correspond to dispatchable units work of messages. Why not? Why not? Why not? Let me challenge that. Let me challenge that. Can we fix that with TCP? Can we fix that? Can I, assuming we don't have a limit in my MTU, right? Assume I don't have a limit in my MTU, right? Because I'm in a data center, I'm going to make, I don't know, 1 gig, my MTU. I don't know if that's even possible. Let's say it is, right? That means my IP packet is so large, right? Can we even have a gig IP packet? 2 to the power, what, 16-bit? So that gives us 65K. That is tiny, dude. So the largest MTU we can get is 65K in IPv4, right? That is tiny, dude. 65K? So that's the largest MTU we can get. All right. Okay. That is tiny. I have to agree with you. All right. But I'm still going to continue my theory here. All right. IPv6. Let's see IPv6. Yeah, dude. Sounds like it's 64K. All right. Regardless. Let's go back. All right. Let's stick with this. All right, so let's say the MTU is 65K because apparently anything larger than that doesn't make sense because you can't fit the IP header. And where did I hear that sometimes the payload is 0? So you put the payload length as 0 and you can put whatever you want there. I'm pretty sure I read something like that. I might be wrong. But yeah, let's assume 65K. Like, don't send any message larger than 65K. All right, let's put some restriction here. So now, the MTU that large, then you have the frame is 65K, obviously, and then you have the IP packet is 65K, and then as a result, the MSS will be 65K minus whatever, 40 bytes for the headers. That's beautiful, right? This way, now you can control each message you send, actually send it in a segment. So now if your message is 1,000 byte, have a low-level API, which I believe you can, flush the segment one segment. It doesn't have to be full. And have your application treat the segment as a message. Can we do this? Can we do this? Is this even possible? I'm just challenging this. I don't know if it's possible or not. If you can, in TCP, treat the segment as a unit of work, then for free, we got the length, you guys. That's the message length. Can we do this? Can we do this, you guys? Maybe not. Maybe yes. Right? Unless if there is like, if middle router tried to play with the segments and retransmit it, I cannot guarantee that. I don't think we can guarantee the segment size, right? If you have proxies, forget about it, right? If you have like end-to-end, the host is behind a proxy, right? And then the proxy is like you're establishing a TCP connection between you and the proxy establish connection with the backend, actual backend. Then the proxy have to rewrite these segments to the backend, right? So you have to make sure the proxy is actually rewriting the same segment sizes, which you cannot guarantee because there is no these are not written in stone as far as I know, right? These segment sizes, it's like whatever you receive won't necessarily go into that, I think. So it might work, it might not, but I guess it's safer to create a new protocol. But I know I would like to give it a try first. It would be better for each message to be dispatched to a different thread so messages can be processed concurrently. So that's another advantage. Now that if the thread knows where the message starts, where the message ends, then it can be, oh, this is one message, here thread take it, here message, one take it, right? That's the same thing. If we somehow can guarantee, that's what I'm saying, right? If we can somehow guarantee a message fitting in a single segment, then we can solve this, right? Can we guarantee that? I don't have an answer to that. Let's read this highlighted that I highlighted in red for some reason. In this word, the NIC should perform load balancing, dispatching incoming request across a collection of application threads via kernel bypass. However, this will not be possible since information about message boundaries is application specific and unknown to transport layer. I think I mentioned that, but I highlighted it here again because it's so important. The fact that the information, the metadata about the message is available at the transport layer is so powerful, which you think about it, the segment does have a size, right? The length of the actual content of the segment. This is how, that's the length of the segment. It does have that, right? The data length, right? But maybe it's not guaranteed, right? That's why we cannot use it, right? But what they are inventing effectively is inventing the same concept of a segment, but as a discrete message here. Obviously, it's more complicated than I'm mentioning, but yeah, if the NIC, for example, knows about the length, it can do the work and then immediately dispatch the message to the thread. All right, we are reaching connection orientation, very critical. So the concept of connections in TCP is, we've talked about this, right? WhatsApp, at some point supported 1 million TCP connection, then they are back to 3, and I believe that now they're more than that, 3 million TCP connection per host, and they are doing their best to make sure that they fit a lot of connection in a single host, TCP connection that is in a single host, right? And that's so they're squeezing as much as possible memory wise, right? But the reason they cannot go more than that is because each connection takes memory, right? It's a long-lived connection states, left and right. There's window sizes, there's the sequences, what kind of the sequence, there are file descriptors, right? And I believe Linux, as they mentioned here, yeah, it's actually they mentioned here. Let's read actually. Connections are undesirable in data center environment because application can have hundreds or thousands of them, resulting in high overhead in space and time. For example, an Linux kernel keeps about 2 kilobytes of state for each TCP socket, excluding packet buffers. Additional state is required at the application level. Yeah, that's a positive point. We talked about this many times. One of the pet peeves in the TCP is the connection is just, it's expensive to keep a connection, a stateful connection at the server, and might I say at the client level as well, right? So yeah, it's expensive to keep a connection. So they don't like that. They want to change that. Facebook found a memory demand for a separate connection demanding. This allows a single connection for each server to be shared across all application thread. A single connection. So they made sure that a single connection is shared across all application threads. Let's continue reading here. Right? So that's what they did. They thought, okay, instead of having a lot of connections, let's have one connection and share it between application threads. Right? So effectively, we're multiplexing, right? That's multiplexing. We're multiplexing with things going into one, right? To reduce proxy overhead, Facebook uses UDP because there is an overhead now that we have with proxies and we have this connection, we have an overhead. So they use UDP instead of TCP to tolerate the unreliability. But this sacrifices congestion control for the UDP. We know that, right? But I believe this is now outdated because I'm pretty sure Facebook completely moved to QUIC. Yeah, QUIC is on top of UDP, but QUIC supports congestion control at the stream level, might I say. So yeah, maybe this paper was written a little bit a while back. The overhead for connection state are also problematic when offloading the transport to the NIC due to limited resources on the NIC chip. Yeah, what you're gonna offload the TCP connections down to the NIC? That's impossible, right? How much memory can you handle on that controller? That's not possible, right? So that I believe they want to move to the NIC. That's from the paper here, the NIC, the network interface controller. They will move everything as much as possible from software to the hardware and make it firmware. Yeah, patching is gonna be a nightmare, but they're gonna take care of it. It's a data center. Who cares, right? Still, security, vulnerability, stuff like that. I don't know, man. Sounds to me like easier to patch an operating system than a hardware firmware, especially if you have thousands and hundreds of thousands servers. I don't know if you thought about that. I don't know if it's a good idea. Yeah, it's fast, but another problem with connection is that they require a setup phase before any data can be transmitted. Sure, we know that. The sense and ACK. Not only that, they didn't mention even the encryption here, like TLS. You gotta have encryption between your data centers, right? So you're gonna encrypt. So yep, there is a handshake going on. I didn't read anything related to encryption when it comes to Homa. Now that I'm actually thinking about it. Didn't read anything related to encryption. Maybe they don't have that. Or maybe they do. Bandwidth sharing. So there's a concept of fair scheduling, which we talked about in TCP. Unfortunately, scheduling discipline like this, which is this fair thing, like a segment is a segment. Hey, you get a segment, I get a segment, segment. So even if the segment is 1 byte and this segment is 1500 bytes, which is full segment, then I'm going to process them in order. I don't care if you might have 1,000 1-byte segments and we have 3 or we have like a couple of longer segments, which is like this actual TCP segment, right? Then the in order is fair. It's like, hey, I don't care if you're short or long. I'm gonna process you 1 byte, then process 1500, then process 1500, then process 1500, up until I go back to you, and then I process another byte. So technically, the shorter messages are starving because you have 10 shorter messages that can be processed in one go, but you have waited because you are fair. I don't know what I'm doing, air quotes. But yeah, so that's they don't like that. So they're shifting to this thing that's called shortest remaining processing time. And basically what that means is that as I am processing something, I want to know like how long are you, how short are you? In TCP, we don't know the length, right, of the actual message. We know the length of the segment, which is useless, right? Right? But we don't know the length of the message. So, but if we do, we could have then, oh, how much are we remaining for this? Oh, we need 1,000 bytes for this, 20. oh, let me just process the shortest, the 20s, and then I'm gonna hit that 1001 hit. So your throughput automatically increases here, right? It's just fascinating stuff. I like to think about all this stuff. That's good stuff. That's good stuff. Provide better overall response time because they dedicate all of the available resources to a single task at a time, ensuring that it finishes quickly. Right? So it's like, hey, single task, let's finish you up, let's wrap it up. Anything that can be, and that comes back to priorities and stuff like that. Again, I highlighted important stuff. TCP has no information about message boundaries. We do not know where the message starts and where the message ends. Sender-driven congestion control. TCP drives congestion control from senders, which voluntarily slow their rate of packet transmission when they detect congestion. We talked about that, right? That's one problem. Another problem of the TCP. Again, a problem for data centers, that is. So we'll continue again discussing congestion control here. They rely on congestion signals related to buffer occupancy. More commonly, switches generate ECN notification when queue length reach a certain threshold. I talked about that, the ECN notification, where if the routers or the switches, again, saying just switches here, to me, a switch is a layer 2 thing. It has nothing to do with layer 3. It doesn't touch the IP packets, right? Again, maybe in the data center they speak this language. To me, it's confusing. You have to say layer 3 switch. You can't just say switch, right? So that's another pet peeve with this paper. It's like, yeah, it's specifically say layer 3 switch, which are switches that look at layer 3, which is the IP protocol, and does stuff to that at that layer, right? Reads the IP headers, which most switches just read, the MAC addresses, the frames, right? It doesn't care about the IP header. So layer 3 switches does a deep packet inspection and determines the IP packet. And when it does that, there is a bit that it can set in the IP called the ECN, which is the explicit congestion notification. It tells as it processes this packet, it will say, hey, I'm about to be congested. There is a lot of stuff in my buffer. It marks it up. So as the IP packets goes all the way to the host replay back that IP packet and sits it in to sit the ECN header in the IP packet, and this way the sender will know that, oh, something happened, congestion happened. But look how long it took, right? For the sender to know there was a congestion. It took a whole round trip, basically. And that's what I mentioned here. It takes about one RTT for a sender to find out about traffic changes. TCP does not take advantage of priority queues in modern network. I honestly don't know what a priority queue is. Now, maybe, again, network engineers let us know in the comment section. Apparently, it's a specific feature in switches that allows certain packets to have a priority over others. Thus, all packets are treated equal, for short messages can get queued behind long ones. And that's a bad thing for data center, because a short message queued behind a long one, the long one will take longer time to process. And when I say process, I don't mean the application actually processing it right in the app. No, I mean just to receive that message, to deliver that message. It takes more time to deliver than a single shorter message. In-order packet delivery, another bad thing about the TCP, as far as this paper mentions. In data center networks, the most effective way to perform load balancing is to perform packet spraying, which is something new to me as well. Packet spraying, if you don't know, is the idea of having you have a lot of packets coming, IP packets that is, and then you just spray it across the different links that you have, like for load balancing reasons. Let's say you have your switch or your router has multiple links, and all of these links eventually they are load balanced, right? And it will eventually lead there. It's a whole mesh at the end of the day, right? If you think about it this way, then you can send the packet number 1 here, packet number 2 here, packet number 3 here. And instead of sending packet, you send packet number 1, 2, 3 on each link. So effectively, you're spraying the packets just like it's a hose, just spraying it. I'm doing that with my hand now, just spraying the hose, right? So what's wrong? Can we do this in TCP? Apparently not. So instead, TCP network must use flow consistent routing, where all the packets from a given connection take the same trajectory through the network. Flow consistent routing ensures in order packet delivery, but it virtually guarantees that there will be overloaded links in the network. Yeah, that makes sense, right? Because you're now everything just goes into the same link, but it creates a hotspot, right? For a connection, it just follows one link. But I'm really surprised to learn about this. Do we really, in the internet, forget about the data centers, I don't have an answer for that. Do routers in the internet actually do that? Do they look at the source and the destination and then say, oh, you're TCP and you're going to this source, so you're always going to take this path so we can ensure in order guarantee? And is that why multipath TCP was invented? Right? Because to take a different path effectively. That sounds like a bad idea if we're doing that. Really, on the internet, that sounds like a bad idea. I don't know anything anymore. Really, we're just doing a sticky session per connection. Yeah, but apparently from this paper, this is the second time I've seen this term, the flow consistent. First, when I read the multipath TCP paper, and then when I read this paper, flow consistent. Sounds like this is what's happening. It's like I can't find information anymore online about these low-level questions. I need to speak to someone who is an expert, not me, obviously. I need to ask someone who actually entrenched with this on a day-to-day basis that knows these answers, because I don't have answers to this, to be honest. So here they say TCP is beyond repair. TCP is beyond repair. Again, one of the problems, consider congestion control, right? And this is the data center TCP. Let's talk about it a little bit. The data center TCP protocol, you remember when I talked about the explicit congestion notification, right? This bit that we set in the IP header. What happens is that bit that tells you there is a congestion. It doesn't tell you anything else. It doesn't tell you how much congestion, how much are we about to be congested, how much byte left. It doesn't tell you any of that. The data center TCP sets more metadata to the sender to make better decisions about congestion. That's all what it is. And if you want to read more about it, it's right here. Yeah, that's the abstract. The data center TCP, just it's RFC for those listening. It's RFC 8257 for those who are interested. So again, they're mentioning here that all of these schemes, all the protocols that try to enhance TCP or recreate TCP are based on the fundamental problem that it is buffer based, right? So if one of the routers in the middle filled up, tough luck, right? That's the only signal, right? Which they want to change that. Buffer is not, just because you're filled with stuff doesn't mean it's time to drop it. They want to change that. They want to flip that. They want to avoid the buffer to begin with. It's very interesting. Let's continue. We're almost there. Now we get to Homa. Homa is a clean slate redesign of network transport for the data center. So the first concept, messages. Homa is message based. It's not biased. It's not streams. It's message based. So at the transport layer, at layer 4, you have access to a message. It's a complete message. When I get you something, it's a complete message. Yeah, that's the work. We're working around a message. The context is a message. Yeah, we kind of got that with TCP. We got segments, but segment didn't really correspond to messages, and that's what breaks this. A client sends a request message to a server and eventually receives a response message. The primary advantage of a message is they make dispatchable unit explicit at the transport layer. This dispatchable unit of work, not a bunch of bytes, right? It's actual message that we can consume immediately, and we can work on it immediately. NIC-based implementation of the protocol could dispatch message directly to a pool of worker thread via kernel bypass. So now, even if you implemented Homa in the NIC, in the network interface controller, the NIC will only give the application a message that it immediately can consume, not just a byte. So the application has to do zero work when it comes to, parsing and doing all this, work that the HTTP protocol does. Oh, content length, blah, 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 doesn't have any of that, right? It's just immediately consume it. Beautiful. It's a commended way. But the moment we work with messages, you guys, forget about video streaming. This is useless for video streaming. This is useless for gaming. The concept of a gaming. Maybe, yeah, well, it depends on the game, I guess. Right? If a game relies heavily on delivering state from the server, then that would be large messages. I take that back. Maybe it might be a good idea for the game. But if you're receiving like a video streaming or live streaming, then forget about any of that stuff. Audio calls, that won't work with Homa, because you'll have to wait for the whole message to arrive in order to deliver it for the application. That is the trick. So if you have a large message, the NIC is buffering this message. I think it should, right? So that's another limitation. Like, what if you have like a large message? Are you gonna buffer it in the NIC, and does the NIC actually support buffering these large messages? So for example, an application cannot receive any part of the message until the entire message has been received, right? So that's a limitation, I guess, of this. But at the end of the day, they are fine with this limitation. And that's what I like about it. They actually mentioned that, hey, this is the limitation. It's not good. It's not great for anyone, but hey, right? No connections. Homa is connectionless. So when I read this, while Homa is connectionless, you guys, it doesn't mean it's stateless. It is a stateful protocol. It has a state stored both in the client and the server about these things that's called the RPC, right? So there is a state, but there's no connection, right? The concept of a connection, there is no connection set up overhead, and an application can use a single socket to manage any number of concurrent RPCs with any number of peers. Again, here they're talking about a scheduling policy. Let's continue. Receiver-driven congestion control. So that's interesting here. So the difference here is the receiver dictates how the sender sends the information in Homa. Interesting. The receiver has knowledge of all its incoming messages. That's true, right? So it is in a better position to manage this congestion. When a sender transmits a message, it can send a few unscheduled packets unilaterally, enough to cover the round trip time. But the remaining scheduled packets may only be sent in response to grants from the receiver. That's what we talked in the beginning, right? So there is, we always send something called the unscheduled packet. So you cannot, first of all, large or small messages, Homa doesn't send large messages at once, like TCP. It's like, oh, let's just send. No, it divides things into two buckets, if you will. The unscheduled packets, which always get sent. The scheduled packets, which is like get scheduled until we get a grant from the receiver to receive them. And that basically, the moment you get a grant, that means we will have the congestion is controlled by the receiver, and this will guarantee almost no congestion, right? Because we know the moment we receive a grant, that means, hey, I'm good to send. What other problems does this cause, to be honest? What kind of problems? I don't know. Maybe the sender will have backed up a lot of scheduled packets backed up, right? And this chattiness, again, going back from the server to the client. Once the first packet of the message has been seen, the total length of the message is known. That's very interesting. So when you send unscheduled packet of each message, we, for free, give the headers, right? And the header includes the link to the message. So the receiver immediately know that they're going to get a bunch of messages, not complete, not necessarily complete. Some of them might be complete, some of them might not. And they get to decide, the receiver get to decide, okay, let's grant this. Oh, these are short. They are already complete. Let me deliver them. These are not completed yet. Let's send a grant for this one. And now you get to choose and pick and choose. So that's interesting design right there. Does it have limitations? I don't know, man. Sounds like keeping stuff in the sender buffer. Yeah, I don't know if this will starve longer messages or not. It might. Out of order packets. A key design feature of Homa is that it can tolerate out of order packets. Sure. I don't care if a message 3 received before message 1. The order of which the messages are sent has no, to be honest, it has nothing to do with the processing of the messages. It's just messages. Why are you blocking message 3 just because message 1 didn't arrive? No, I get to choose. Like, okay, I might block message 3 because message 1 is short and I have to arrive message 1 first. So yeah, message 3 is very long, so yeah, you can wait. It's okay. But message 1 is short and I want to process shorter packets. So all of this can be actually controlled. So out of order packets are so fine in this case. But again, as long as we have enough information delivered to us so that we can see these messages to begin with, right? All right, so getting there from here, almost done. Conclusion, almost done. So again, Homa, because of all the scheduled and unscheduled and grants, it has its own API and it's not compatible with TCP. So what those guys did, they said, wait a minute. Yeah, sure. Nobody, who's the last one who built on top of TCP? Yeah, some application built directly on TCP, but most people use APIs that sits on top of TCP, such as gRPC, Apache Thrift, right? Those are built on top of HTTP2. gRPC is built on HTTP2, which uses TCP, right? And there's an ongoing backlog item in gRPC to use HTTP3. And now, those guys are working with gRPC team, the Google team, to support Homa as a gRPC transport layer. In this case, the moment Homa comes to gRPC, immediately all the applications light up. And that's the beauty of this. If you are a gRPC user, you're going to get Homa for free if this gets implemented. By the way, did I mention that they have a Linux implementation already? So those guys already did the work and they showed the numbers. So yeah, not all applications. HTTP. Do I see HTTP on top of Homa? HTTP 4 maybe? Because HTTP has nothing to do with streaming. Wait a minute. No. We can't use messages on top of HTTP. That's just not a good idea. Because HTTP is a streaming also. The same concept, right? Imagine like you don't see the page until everything is loaded. No, I want to see as things arrive, especially HTTP streaming and video. We watched YouTube videos. No. Keep this away. keep using TCP and QUIC. No. HTTP 3. That's it. No. Bad idea. I don't think it works for the web, Homa. I don't think it does. So yeah, this is their proposal. They're gonna use gRPC. Let's read the conclusion and end this video. I know you guys are tired. I am also exhausted. I think it's one of the longest videos I made ever. But let's read this, the conclusion. TCP is the wrong protocol for data center computing. Again, they focus on the data center here, right? Nothing to do with other stuff. Nothing to do with the web. Data center computing, TCP is wrong. They want a low-level protocol, a transport protocol that fixes these problems, which they articulated very well in this, in my opinion, in this paper. Obviously, this paper doesn't have details about Homa. If you want the actual details of Homa, there's like a lot of more detailed paper that I'm gonna reference as well. that reads like the actual in the weed, if you want to go that far. Every aspect of TCP design is wrong. There is no part worth keeping. Again, wrong for the data center. There is no part worth keeping. If we want to eliminate the data center tax, we must find a way to move most data center traffic to a radically different protocol. Homa offers an alternative that appears to solve all of TCP problems. The best way to bring Homa into widespread usage is integrated with RPC frameworks. With RPC frameworks that underlie most largest scale center applications. Like, yeah, in microservices, basically, most of this stuff uses gRPC. Any communication between services actually uses maybe gRPC. That's pretty much it. That's the de facto, right? Isn't it? So yeah, this was the "We Need a Replacement for TCP in the Data Center," right? Written by Professor John Ousterhout, Stanford University. Again, paper is still currently under submission, but didn't prevent us from actually reviewing it and reading it. I think it's a good protocol. I think it's a good idea for the data center. That is, does it fix all our TCP problems? No, I think TCP is still relevant. I think we still need the TCP protocol. Yeah, but it's not applicable for everything. It's applicable for certain use cases, especially if you have this request response and responses, and your responses don't have the concept of streaming, right? So in the web, I don't believe this is good for us. Yeah, HTTP is a request response system, but the response, I cannot think of waiting for the whole response to arrive in order to just deliver it, right? I want to see the HTML headers. I want to see the body. I want to see the skeleton comes in, right? As content comes in, let me this idea of streaming the HTML page, whatever you see is what you get, is important. We need to see stuff, right? Unless you just want to click and then just have a loading screen and then just poof, everything appears. You can do that, but I don't know if that will fly in the web, right? And that just did on arrival when you like watch a YouTube video or stuff like that. This is not suitable for streaming videos, right? Because the main disadvantage is we have to have a message, which we don't have this concept in TCP. TCP is just whatever is bytes. It's bytes streaming data. It's just like a hose filled with data. And there is a disadvantage or advantages for this streaming concept. So it really depends on you, what do you want, what's your use cases. I enjoyed going through this. I think it's a good paper. Guys, what do you think about this paper? What do you think about this Homa protocol? Do you think we need it? Do you think we don't? In the data center, again, in the data center, outside, they don't address anything outside at all. But let me know. What do you think? I'm going to see you in the next one. You guys stay awesome. Goodbye.